Okay, here we go. Talking about negative exponents. So we have looked at all kinds of different exponents so far, but they have all been either positive numbers, so, you know, like 1, 2, 3, and these exponents just work the way we kind of want them to, like repeated multiplication. And then we've also looked at 0, which is the first weird exponent we've looked at, and remember the zero power rule, anything to the power of 0 is equal to 1. So we're going to go into now this new kind of universe of negative exponents, and I'm going to just do a couple problems here, and we're going to see what happens. So the first one I'm looking at is this. I've got and these are the same problem, but x squared divided by x to the fifth. So I'm going to use the power rule for quotients. Remember, power rule for quotients. And that says if I take my numerator and I divide that by something, I'm going to subtract those exponents. So this, because it's x squared divided by x to the fifth, I'm going to have x to the power of 2 minus 5. Now you might see where this is headed, but we're just going to go boldly forward. 2 minus 5, of course, is negative 3, so I get x to the power of negative 3. So that's one way to think about that. Another way, over here, I'm going to think about this using just kind of the old school way, where I have x squared on top, so that's repeated multiplication. I have x times x. Then on the bottom, I have x to the fifth power. That's also going to be repeated multiplication. So I have x times x times x times x times x. And now I have some cancellation that can occur. So this x is going to cancel that one. That's going to cancel that. And what's left up top is 1. And what's left on the bottom is just 1, 2, 3 x's. So 1, 2, 3. So my final answer then is 1 over x cubed. And so now the first thing we have, the first result we're going to have down here with negative exponents is basically what we just found, that these two things are the same. So these are the same thing. And I'll show you the theorem here. Okay, if a is a real number, so a is just any real number, and in this class that's pretty much anything we're going to deal with, other than 0, so it can't be 0. 0 to the power of n just gets kind of weird. And n is some integer. And so remember, when I talk about an integer, I'm talking about if n is an integer, it can be like negative 3, negative 2, negative 1, 0, 1, 2, 3. So like numbers, but also the negatives of those numbers. Then, and this is the big deal, a to the power of negative n is equal to 1 over a to the positive n. And this goes both ways. If I have 1 over a to the negative n, that is the same as a to the power of positive n. One thing that I think can help this make a little bit of sense is I'm just going to put in, and these are not required, but remember, if something isn't a fraction, I can think of it as a fraction kind of by just making it over 1. And so here, I think this kind of helps. You can see that this negative exponent in the numerator went downstairs, so it was upstairs, it went downstairs, and then that exponent became positive. Here I had a negative exponent in the denominator, so I had negative downstairs. When it went upstairs, that exponent became positive. So I want to talk about one more way to just think about what is going on. Because so far when we talk about exponentiation, in the past I've talked about it as repeated multiplication. So here, I'm just going to talk about some powers of 2. Here, some powers of 2. 2 to the third power is 8. 2 squared is 4. 2 to the first is 2. And 2 to the 0, we know from that 0 power rule, is 1. It's always tempting to say that that's 0, but it's not. So in the past, when we talked about exponentiation, we think about adding more factors of 2. So we're used to thinking about going up like this. When I go from 1 to 2, I multiply by 2. When I go from 2 to the first to 2 to the second, I multiply by 2. So I'm adding factors of 2. But what we can think about when we're moving down into the negative exponent territory is if I go this way, to get from 8 to 4, I divide by 2. To get from 4 to 2, I divide by 2. To get from 2 to 1, I divide by 2. And this is going to help me, this idea, once I start thinking about guys like this, 2 to the power of negative 1, 2 to the power of negative 2, 2 to the power of negative 3. What's going to happen there, to get from 2 to 1, I divided by 2. What happens if I divide 1 by 2? I get 1 over 2. If I divide by 2 again, I get 1 over 4. 1 over 8. And you can see this pattern continues. 1 divided by 2 is 1/2. 1/2 divided by 2 is 1/4. 1/4 divided by 2 is 1/8. So that's another way it might help to just kind of understand what is even going on. Because this is one of the things that sometimes people are like, come on, negative exponents, what is this? You made this up. We didn't. It's real. Okay, so here are some quick examples of some problems that you will see. Here I have 3 to the power of negative 2. That's just going to become, right now, this 3. You can think of it as being upstairs if that helps. The 3 has a negative exponent. So it is going to go downstairs and have a positive exponent. Here I've got 2 times x to the negative 3. Now what's tricky about this is, remember, this 2 is connected to x to the negative 3 by multiplication. And so that means here that exponent of negative 3 is only going to the x. 2 is happy. In fact, the power on 2 is positive 1. So this 2 is just to the power of positive 1, because anything that isn't being raised to a power is raised to the power of positive 1. So that means the only thing that needs to go downstairs here to make that negative exponent positive is the variable. So that 2 stays upstairs, and that x comes down, and it comes down as x to the power of positive 3. And that is my final answer. Okay? Okay, here I have another one. 1 over 3 to the power of negative 4. Now this is a case where that 3 is being affected by this negative exponent, so it is going to come up, and when it comes up, that exponent becomes positive, and then the only thing left downstairs is 1, so that would normally just be written as 3 to the power of 4. Here I have x to the 5th over x to the 7, and now there's a few ways to do this. I'm going to do it a couple. Let's have a pink way over here. I have, I'm just going to use these rules I've been learning in this section. So this x to the negative 5 is going to come down. So what I have is 1 over, and then I've got that x to the 5 that came downstairs, now has a positive exponent, and then that x to the 7th was happy downstairs, so it stays where it is. And now I have my rule, product rule for exponents says that x to the 5th times x to the 7th. What I'm doing is counting factors of x. I have 5 over here, I have 7 over here, so I end up with x to the 12th. That is one perfectly good full credit way to do that problem. Another way, let's have the, I don't know, orange path. We go over here. Now, if I have, that's going to be too light, x to the negative 5, I can use the quotient rule for exponents. X to the negative 5 divided by x to the 7. So x to the negative 5 minus positive 7. I end up with x to the negative 12. And then when things are fully simplified, they should be written with no negative exponents. So you want to put that x downstairs in a fraction so that that negative exponent becomes positive. Okay, let's move on to the next page. Okay, here, so this is where we have all these rules happening at the same time. Things get a little nuts. Here, I've got two things, and I'm going to go and just kind of clarify that this is y to the power of negative 3 times z to the power of positive 6. And then that whole thing is being raised to the power of negative 6. So the operation connecting these two things is multiplication. And because both of those things are getting raised to a power in parentheses, that's going to be the first thing. So y to the negative 3 is going to get raised to the negative 6. And then z to the 6 is going to get raised to the negative 6. And now when I take something that's being raised to a power and I raise that to a power, I multiply those two exponents. So I have y to the power of negative 3 times negative 6 is positive 18. And then z to the power of positive 6 times negative 6 is negative 36. And that is my fully simplified answer. Whoa, no, it's not. Oh, that's good. That's good. So this was exciting. It felt good. It looks good, right? But what's wrong? This should be rewritten with a positive exponent. So my y to the 18th stays up top. And the z to the negative 36 goes downstairs and becomes z to the positive 36. Everybody's happy. This is my real fully simplified answer. There we go. Okay, here's another one. I've got a quotient. So there's a bunch of stuff happening here. I've got some stuff in my numerator, some stuff in my denominator. That quotient is being raised to a power. So what happens is that means my power rule for quotients, I believe, says 3a squared. That is going to get raised to the negative 3 power. So the numerator is going to get raised to that power. And then also that denominator, b, is going to get raised to the negative 3. Whoops. Oh, whatever. And now, downstairs, this is going to be easy because it's just one thing raised to one power. Upstairs, though, I have to remember that this negative 3, these things are connected by multiplication. So that's going to go there and there. So I end up with 3 to the power of negative 3. A squared to the power of negative 3. And then downstairs, I have my good friend b to the negative 3. And before I start worrying about who's going to go where, I'm going to get that thing nice and simplified. So I have 3 to the negative 3. A to the power of 2 to the power of negative 3 is going to be a to the negative 6. And I have b to the negative 3 down here. And now I have a situation where everybody is unhappy. Everybody has a negative exponent. One thing that people get excited about is they'll often try to say that 3 to the power of negative 3 is negative 27. And it's not. It's going to be positive because this has nothing to do with the sign. The sign of the exponent has nothing to do with the sign of the answer. So now all these guys, this is going to go down, this is going to go down, and this is going to come up. And so my final answer here is b cubed. Well, this isn't even my final, actually. Over 3 to the third times a to the sixth. So you can see everything switched to the other side of the fraction bar, and that made it positive. And now I can simplify that b cubed is 27 times a to the sixth. So that is my final answer. So you have to be careful about when to stop. Both of these, I kind of thought I was done before I was. So stay on your toes. Here, I've got a bunch of stuff happening. And again, just like that previous problem, there's two ways I could do this. The first way is I could get all of my exponents sorted out right away, or I could dive right in and start dealing with my quotient rule. So like here, I've got my 4s. So I have 4 to the negative 1 over 4 to the negative 3. And then I have x to the negative 3 over x squared. And I have, so all I'm doing right now is rewriting y over y to the negative 6. So anytime I have the same base to different powers and those are being divided, I can subtract those exponents. So this can be 4 to the negative 1 minus negative 3. And this, whenever you're writing something like that, that should be a cue to kind of slow down and be pretty careful because a lot can go wrong. Negative 3 minus positive 2, and then y to the power of 1 minus negative 6. Now I just have to really, negative 1 minus negative 3, that's negative 1 plus 3, so 2. Then I have x to the power of negative 5, and y to the power of 1 minus negative 6 is 7. Now, these guys are happy, but this has a negative exponent, so it's going to want to go down. So what I end up with is 4 squared is just 16. X to the 5th is going to go downstairs. So it was negative upstairs, it goes downstairs, it becomes positive. And then my y to the 7th stays up top. And that's complete. And now we've got this guy. So now this is a type of problem that can cause a bunch of trouble. Generally, especially if you have an exponent out here, it's going to be easier to try to simplify everything that's inside first. So before I deal with distributing that 3 to everything, I'm going to see if there's anything I can do inside. And as you might imagine, there is. So I have just this 2 that's hanging out on top, negative 2. Then I have x cubed, and then I have x to the first down here, and then I have y, and then I have y to the negative 1 down here. So now later I'm going to have to take all this stuff and raise it to the power of 3, but for now I can just do some simplification of what's hanging out inside those parentheses. So I have negative 2, then I have x to the power of 3 minus 1, and then I have y to the power of 1 minus negative 1. And then I just want to remind myself that I will eventually be cubing that whole thing. So I have negative 2x squared y to the power of 2 and now I just have to distribute that 3. So I have negative 2 to the power of 3. And the reason I'm doing that is because all of these things are connected by multiplication. So x squared cubed, and then y squared cubed. Now, negative 2 times negative 2 is positive 4, times negative 2 is negative 8. X squared cubed is x squared times x squared times x squared, so x to the 6th. And then I've got the same thing, y squared cubed, that's also going to be y to the 6th. And that is my final answer. We've got some group problems on here that you guys actually have in your packets as group problems. But what I'm going to do is, like I've been doing, just post those solutions. And in the meantime, I'll move on to page 3. Okay, so now in the second part of 5.5, we have this big idea of scientific notation. And scientific notation is something, now that we have negative exponents, we can go all the way into it. It's helpful for dealing with numbers that are either very, very large or very, very small. We have this is the number of the distance between the Sun and Pluto in kilometers. So, distance between the Sun and Pluto in kilometers. And it's not like you're going to need to memorize these numbers. It's just, these are like, this is something that really comes up in actual math. And I always think it's worth kind of mentioning that. This totally ridiculous number, and I think this number is a really, really good motivator for scientific notation, because this is impossible to look at, in my opinion. What it is the mass of a proton. So this is the mass of a proton in what? Grams? Grams. And the mass of a proton and the distance from the Sun to Pluto, these are the kinds of things that come up. You know, if you're doing science, this is something that might be a part of a paper that you're trying to write. And what we want to do is have a way to talk about these numbers without making people like sit here and count all these zeros and lose their minds. Especially with a number like this, if I were to have a number, you know, if this was on one page of a paper and on the next page I had a number that had a couple, you know, a different number of zeros, it's almost impossible for anyone to tell. So you want to be careful of that. So here's the deal. Scientific notation is what we're going to use to deal with this problem. A positive number is written in scientific notation if it is written as the product of a number a, where a is greater than or equal to 1 and less than 10. So all that means is it's between 1 and 10. So for example, like 1.56 or 9.94 or 3.0. All of these are okay. Numbers like this, 0.56, that is not greater than 1. So that is not what I'm talking about. And numbers like 11.4, that's not what I'm talking about, because that is bigger than 10. So it's always a number and then maybe some stuff behind the decimal. So that special number a, and then the form of scientific notation is very, very fussy. So multiplication, and the multiplication in scientific notation is written like an X, which you probably remember from your youth, but is generally not a good idea in algebra because there are variables all the time. But this is just how scientific notation is, and it's too late to change it, so this is what we're doing. And then that power of 10 is raised to some power. So this is the form of scientific notation. And the reason scientific notation is helpful is because if I have some number, and this is kind of cool, if I have like 14 times 10, the way I do that is I just add a 0. And if I have 14 times 10 to the negative 1, that's the same as 14 divided by 10, and that is 1.4. So because we have a base 10 number system, multiplying by 10 to positive powers just moves my decimal place to the right, and if I multiply by 10 raised to negative powers, that's the same as dividing by 10, so that just moves my decimal point to the left. And that's what we're going to exploit for this notation. So to write a number in scientific notation, I have these steps. My first step is move the decimal point in the original number to the left or right so that the new number has a value between 1 and 10. Then I'm going to count the number of decimal places I moved that decimal point during step 1. Count the number of, if the original number is larger than 10, the number is positive. And if your original number is smaller than 10, like a really small number, you know, like this outrageously small number. So if the number is smaller than 10, the number is negative. So then all you're going to do is take the number you found in step 1 and then multiply that by 10 raised to the power you found in step 2. So I'll do a couple examples here. 5,906,000. I have, so I'm going to move that decimal point to the left. Starting here, so I go 1, 2, 3, 4, 5, 6, 7, 8, 9. So I moved it 9 places to the left. So now my number A is 5.906. So I want to contain all that number information, but then if there's just a bunch of zeros, I don't have to write them. Now this gets multiplied by 10, and that 10 is going to be raised to the power of the number of times I had to move the decimal, so 9. And because this number is big, that's going to be 10 to the positive 9. So I have that. Now here, and this one's kind of rough, I'm going to actually zoom way in here. So I can try to not, okay, so I'm all zoomed in. Hopefully I won't lose my mind trying to count all these decimals. So I start here, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And that is where I'm going to stop, because this gives me my A of 1.65. So now 1.65 contains all of the non-zero information in here. And then the only thing is I need to multiply that by 10 raised to the power of 24. But because this number is really small, that has to be 10 to the power of negative 24. And this is my answer. And you can see this is a lot easier to deal with. I can just look at this. This tells me how small the number is. If I had a number that was 100 times smaller than this, it would be times 10 to the negative 26. And so you could just look and be like, oh, that number is more negative. That's a smaller number, instead of having to try to count zeros. Then I've just got one more problem here. This one isn't too crazy. I'm going to move this decimal. My A is going to be 3.67. And that decimal is going to go 1, 2, 3, 4, 5, 6, 7, 8. And it's going to be times 10 to the positive 8 because that number is big. So the next couple examples here are converting to standard notation. And standard notation just means like regular notation. So I have something like this where I have 1.02, and I just like do the opposite of what I did up top. So this is getting multiplied by 10 to the 5th, so I'm going to go 1, 2, 3, 4, 5. This is going to be the new home of my decimal point. all of these little loops are going to get filled with zeros, and my number in the end is 102,000, so 102,000. So that's in standard notation. Here's another one. I start with my 3.007, and now this, because that's negative, I'm going to move that decimal place to the left. This number is going to get smaller. 1, 2, 3, 4, 5. And then again, all those little empty loops. And so my final number is 0.00003007. That's in standard notation. And then there's a few of these problems where what's cool about this is I can use my rules of exponent. So I have 8 times 7. I can just do 8 times 7, and then I can multiply my powers of 10, so to the times 10 to the power of negative 6 times 10 to the third. So, because all that's happening here is multiplication. So I end up with 56 times 10 to the negative 3. So that means I take that 56 and I'm going to move the decimal 1, 2, 3 points to the left. Have some zeros. 0.056. There we go. Okay, on to page 4. Okay, so this last page we've just got chapter 5, section 6, and we don't cover much of this section, so I thought I'd just put it in here. So remember, from addition of fractions, if I have two fractions and they have the same denominator, so if I have like a over c plus b over c, if those have exactly the same denominator, I just add across the top. So I have a plus b over c. So the reason that this is getting brought up is this goes both ways. So when I divide a polynomial by a monomial, what I do is I divide each term of that polynomial by the monomial. And I'll show you what I mean here in a second. Divide each term of the polynomial by the monomial. So basically it's like this. Here, if I'm taking a plus b and dividing that by c, that's the same as just dividing a by c and then dividing b by c. So I have a plus b over c equals a over c plus b over c. And this is just a rule you already know backwards. So here's a couple of examples. If I have like this polynomial, so here's one polynomial, and that whole polynomial is getting divided by 2m. So what they're talking about is 6m squared plus 2m. And that whole thing is getting divided by 2m. Can't decide whether to make my m's fancy or not. I'm going with fancy. So one of the most dangerous things that happens in algebra is people want to cancel these. Because like, oh, I got 2m upstairs, I got 2m downstairs. The thing to remember is that these things are connected by addition. And that cancellation only works when multiplication is the only thing happening. So I get 6m squared divided by 2m. Plus 2m divided by 2m. And so now, these are just two problems I can do. So now over here, I've got a 6 upstairs, I've got a 2 downstairs. Those are going to cancel because I've just got multiplication, and I end up with a 3 upstairs. And then I had 2 m's upstairs and 1 m downstairs. So I end up with just one factor of m. That's m to the power of 2 minus 1. Now over here I have a 2 upstairs, a 2 downstairs, an m upstairs, an m downstairs. If everything cancels out, what's left? This cancels to 1, that cancels to 1, so it's like 1 over 1. So I end up with 3m plus 1. It's tempting to think that if things fully cancel, it should be all gone, but it's down to just the multiplicative identity of 1. And then I've got one more here. So this is just another one of these types of problems. The first thing I'm going to do is break it down to 3 monomial division problems. 9x to the 5th, that first thing divided by 3x squared. And then the second thing divided by 3x squared. It's a lot like how the distributive property works with addition. We're just going over, we're dividing a bunch of things, a bunch of different terms instead of multiplying a bunch of different terms. So now that 9x to the 5th, 9 is going to cancel down to 3. 3 cancels to 1. And then x, so I have 3 times x to the power of 5 minus 2. Well, 5 minus 2. You have to be careful with that kind of thing, because that can, you know, I'm doing a bunch of, now I'm moving on to this, and if I would have left that, it would have been easy to have 3x to the 5th minus 2 instead of 3x to the 3rd in my final answer. And you'd be surprised how much that happens to people. So I end up with 4. And now my x squareds completely cancel out. So those cancel completely out. So I just have 4 by itself. Plus, these 3's cancel. And then I have x to the power of 1 minus 2. So when I go through now and simplify everything completely, I have 3x cubed minus 4, and then x to the power of negative 1. And so for my final answer, I should write that with only positive exponents like this. 3x cubed minus 4 plus 1 over x. If you're confused about how that canceling is working, I'm just going to do a quick little example here. So like 12x squared over 3x squared. Here's what's happening is 12 is 3 times 4, and 4 is 2 times 2. So that means 12 is 2 times 2 times 3, and then x squared is x times x. 3x squared is 3 times x times x. So then anything I have both on the top and on the bottom cancels out. And you can see all that's left on top is that 4, and that's where this 4 comes from. All right, that's it for Chapter 5.